Evening. Oops, there we go. Good evening. Welcome to your Thursday evening stroll around your celestial neighborhood. I'm Irene Pease, your friendly neighborhood astronomer, coming to you from an undisclosed location outside of Brooklyn. Hoping that things go better this week than they did last week, but every week is just a new fun adventure. Um, as indicated by our Pac-Man Earth in the background. So thanks for tuning in. Again, this is just kind of my outlet as I'm kind of dealing with, all the things in our lives that we deal with. So this week, I'm continuing. I didn't quite get everything pulled together from last week. That might still happen this weekend. High hopes. But this week, the plan is to look at the universe in some different wavelengths. Again, I'm kind of following along with another astronomy class that I'm teaching. And this week we talked a little bit about the spectrum and spectra and Kirchhoff's laws and all those fun things that we're not quite going to get to here. But we will look at some different Allsky surveys at different wavelengths of the electromagnetic spectrum. So just different types of light. And so you can see what the sky would look like if you had eyes that were sensitive to different types of light. So I managed to load in one extra map just this evening, like I do, and kind of excited to talk about that. It's not the best resolution, but whatever, we'll see. Anyway, I'm just going to be using OpenSpace tonight. Again, try to keep it simple. We'll see how it goes. You can see OpenSpace in the background right now. So this is open source software that you can download for free at openspaceproject.com. And again, it's open source, so you can tinker with it like I do, and you can like put stuff in and modify things and build things and whatever. So it kind of comes with a whole bunch of data already, like including the Digital Universe Atlas, which is curated at the Museum of Natural History in New York City. And so, yeah, but I just, grab some data from wherever and just stick it in there, and we're going to play with it. That's kind of the plan. Yeah, Faisal's saying, yeah, open space. You can't take the sky from me. I like it. I like it a lot. All right. So I guess first things first, just kind of remove some of the text here. So just plain, there's open space. So just talking first about the light spectrum and what we mean by the electromagnetic spectrum. So electromagnetic spectrum, I mean light, and there's light of all different wavelengths, all different frequencies. So this is kind of a big range. This is a little NASA image. Thanks, NASA. So you can see and scales don't really mean a lot here, like how big or how small different ranges are. It's kind of, fudgy. But we can see where visible light lies relative to other types of light. So the red waves, those are the longest wavelengths, the lowest frequencies, lowest energy light that our eyes detect. And then the blue and violet, those are the short wavelength, higher frequency, higher energy parts of the electromagnetic spectrum that our eyes detect. So past the violet, we have ultraviolet. So that's more energy. So that's like bad for you and living things. And then we get into even worse light for you, the X-ray. So yeah, if you need an X-ray, get an X-ray, but don't get it, just for fun, like snapping selfies and X-rays is not a good idea. And then beyond that, we have gamma rays. And I think they even have like cosmic rays that are even more dangerous and higher energy than that. Okay, so we don't really encounter a lot of these in our daily lives. More on that in just a minute. Past the red, we have infrared. That's why we call it infrared, past the red. And then past that, astronomers might make up other subcategories here, but we're just going to say microwaves. So like your microwave oven, if you have a microwave at home, it produces wavelengths of light that are in this part of the EM spectrum. And then past that, radio waves. So we use radio waves to send signals to communicate across large distances. And there's a reason for that, because they're low energy, long wavelengths. So they just kind of travel well for that kind of thing. So the other really cool thing you see here, you see like kind of these applications and how does this relate to you. Um, the other thing that we see here is what makes it through the atmosphere, right? So if the universe is broadcasting at this entire spectrum, we can't even see all of it from the ground. So even if, people had telescopes ages ago, they would never be able to see ultraviolet, well, not much ultraviolet, X-ray or gamma rays, because those don't make it through the atmosphere. The atmosphere is opaque to those wavelengths. So we have this kind of optical window where visible light gets through and some infrared light gets through. It's kind of a little bit here and there. And then a lot more of the higher range infrared and some microwaves are blocked out. And then we have another radio window where we can receive a lot of radio waves from the universe. And then the longer waves of those are also blocked out. So as far as ground-based telescopes, we have a lot of optical, little into the infrared, and then we have radio waves. But everything else for the microwaves, for the UV, X-ray, and gamma rays, we have to put satellites in space. So that's why we have space telescopes. And just for kicks, because clouds are crap, we also have optical telescopes in space. I don't know that we have any radio telescopes in space because you need like a really big dish for that. So yeah. So all the others we basically stick in space. So you may have heard of Hubble, and I might mention just a couple other satellites that are collecting information about the rest of the universe for us, way out there. Some are in like low Earth orbit, just kind of orbiting around nearby, and then some of them are a bit further away. I can just come around here. Some of them are a bit further away. Yeah, like out at like Lagrange points and whatnot. So yeah, but out looking at the universe. So really what I want to do for now is turn off that, and we're going to turn off the Earth because we don't really need the Earth much right now. So goodbye Earth and Earth atmosphere. There we go. And now we're just out in space, more or less. So this is already kind of an Allsky survey where basically I'm going to tilt us so that we're kind of looking the other way along the plane of the Milky Way. So we can learn about our solar system by looking at different types of light as well. But for the most part, we're looking, beyond the solar system. So we might be looking out into the galaxy. So this is our galaxy as seen from Earth. An all-sky survey, basically, where we just look all over the sky and make a map of all that. And this is just a visible light that our eyes can detect. So you notice that there's kind of like this plane of the Milky Way that we see along here. There's some light spots. There's some dark, kind of dusty spots. So those are bits that are kind of opaque to our eyes. This dust kind of blocks the visible light, and actually I can make it a little bit brighter, exaggerate it a bit. One of these. Hold on to your hats. Whoosh. All right, so there's a kind of artificially, optically more bright Milky Way. I guess we could turn off the sun too. Let's turn off the sun. Sun's getting in the way. That's not just like another galaxy or something. Yeah, turn off the sun. So kind of just like white, like lots and lots of stars. So if you scan that part of the sky with your binoculars or telescope, you'd see lots of little dots. And then also some pink blobs and some other fuzzy bits. So a lot of the pink blobs, those are huge clouds of gas where stars are being born. And then some of the other kind of sparkly blobby bits might be star clusters where stars have formed. But yeah, that's kind of our galaxy. And I think we even saw a little bit of some other galaxies. I'm going to just kind of increase the field of view a little bit and see if we can open this up to see just a bit more in here. a slightly wider field of view. And we should be seeing kind of the Magellanic Clouds drifting through there at some point. So a couple other galaxies. So here's like the Andromeda Galaxy. That's a relatively close by, relatively large spiral galaxy. And we'll see um, the other two, the large and small Magellanic Clouds, those will be coming by as well in a little bit. So yeah, so that's our visible. So we can see this, with our eyes. We can use whatever ground-based telescopes, nothing super duper fancy to see all of this. But I want to go ahead and I'm actually going to wait for the Magellanic Clouds to come by here. And we're going to venture out. We're going to start with the low wavelength part of the spectrum and then work our way up from there. So I think we're getting a Magellanic Cloud down here. So I'm just going to pause. Peek down here. I'm pretty sure it's the large one. Yep. The large one is the, bigger one. And there's the small. So our two kind of neighbors in space. So actually, as I scoot back up here, this kind of rolling view that we'll use, I might need to bring the window out a little further. Wow. It's too far. All right. So we'll just leave it so we can kind of see a little bit of the large cloud when that goes by. So this is like 100-degree field of view that we're looking at because I know you wanted to know that. There we go. So some of the longest wavelengths that I have in here is this new data set. It's not like new, it's just new for me. I just popped it in here like you do when you tinker with open space. This one, yeah, this one, yeah. So this is atomic hydrogen. We're going to make that really bright. Yeah, that's pretty bright. So this one may not be exactly aligned because I just kind of dumped it in here this afternoon. And I'm just going to dim the Milky Way a little bit so it's not quite as much back there. So we can still see some of the background stars and stuff for reference. So like you can see like this little pink blob. So I didn't align it exactly. Like this little pink blob should be matched up with the Andromeda Galaxy. So you can still kind of see a little bit of the visible in the background for reference. So atomic hydrogen gives off this wavelength at 21 centimeters. And so that's not like a crack in the universe that you're seeing here. That's just a seam in the data because, again, it wasn't perfect. I just kind of threw it in here. But what we're seeing is a bunch of gas. So this is a tracer for just atomic hydrogen, just neutral hydrogen that's hanging out by itself, not linked with another hydrogen atom, just out there in the universe. And really, the brighter colors, that's where there's more of it. And so we're going to see there's a bunch down by the Magellanic Clouds. There's a whole blob down there. So brighter, I should say more intense, means that there's more of it. But then the actual coloring is a little bit odd. It's actually kind of a velocity map. So I might actually scale this out a bit more because this is pretty cool. Velocity map. So I'm going to pause this and we're going to see if we can make like a really huge field of view here. Huge field of view. Blah. Okay, so it's all stretched out and whatnot. All right. So at this point, we're basically looking in, I think, is that the center of the galaxy? Let me just check with if I blink this off and on. Yeah, that's basically the center of the galaxy. All right, so this is our galactic center over here. These are like, ignore that there's like moons going around a planet or something. So ignore that. All right. So center of the galaxy. So you see kind of slightly green on one side and slightly blue on the other side. And then we see more blue out here and then more green out here. And in between it kind of goes neutral. So the greens and any yellows, if you see yellow, so like down by the Magellanic Clouds, those are things that are moving away from us. And then the blues and any pinks, so like we saw the Andromeda Galaxy was pink, those are parts, that's where the gas, the atomic hydrogen is moving towards us. So with this velocity map, we're mapping the relative speed basically of this gas towards or away from us. And this kind of tells us where we are in the galaxy, because remember, everything in the galaxy, if I turn off this thing real quick, and I'm going to turn on the constellations. This is a super cool thing. All right. And then we're going to zoom way out, away from the sun. Zooming out from the sun. Oh, and I forgot that we're at a ridiculously high field of view. So we'll go back to a less ridiculous field of view. Sorry about that. All right. So we zoom out away from the sun, away from the solar system. Off we go out into space. And so here we are. There's our gorgeous galaxy. All right. So we were looking in towards the center of the galaxy, right? So some of the stuff, basically, if we look at the galaxy face on, we're seeing the stuff between us and the center that's moving ahead of us, that's moving away from us because this inner stuff is spinning faster. So this stuff is moving away and this over here is moving towards us. And then on the outer part of the galaxy, for the stuff that's further from the center from us, that stuff is going to be kind of moving towards us because we're moving faster in it. So this stuff looks like it's moving towards us, and this stuff looks like it's moving away from us. So this basically tells us about the galaxy's rotational rates. There's a really cool map actually with Gaia data that shows the same thing, looking at the radial velocities of stars. But we've had this kind of map with this. This is from like the late 90s, I think. This map was made using two different radio telescopes, one in Effelsberg, Germany, to get the northern hemisphere, and the other one, a 64-meter Parkes telescope in Australia, to get the southern hemisphere. So it is, again, an all-sky map. But yeah, that's the kind of velocity that we can see by mapping all this gas that's out there. So kind of a cool thing. We can tell just by kind of tell the structure and what's happening in our galaxy by mapping this gas, which is pretty neat. So we'll come back in home a little ways. So I could go on about this for a little bit, but I feel like I already need to move on to some of the other maps, or I won't get to any others tonight. So let's reset. I think this is normally about an 80-degree field of view. That should work for now. And we're going to go back to our all skies, and we're going to go all the way out. We're going to go through a little bit of a history of the cosmic microwave background. So this is going to be a shorter wavelength. It's still, I guess the 21 centimeter, we would consider that to be radio. But then the cosmic microwave background, we consider that to be microwave, which is why we call it microwave. So I'm going to go ahead and turn on one of our older maps. If I can get it to load. There we go. Boom. Okay, that's big and blurry. And actually, maybe for this one, we should zoom out to the edge of the universe, but I'm not going to, because we always do that. So this is the CMB from COBE, the Cosmic Microwave Background Explorer, from way back in the day. So this was our kind of first attempt at an all-sky map of this feature of the universe, like this baby light from the first time that light could travel in the universe. And so these different colors represent tiny, tiny changes, tiny, tiny differences in the temperature of the early universe. We're talking about differences of a millionth of a degree. So very slight, but there was some differences. It wasn't exactly uniform, but pretty much uniform, considering these differences are like millionth of a degree. So at some point we said, yeah, how about something that's like slightly higher res? So we came up with the Wmap, that stands for the Wilkinson Microwave Anisotropy Probe, which is exactly what it sounds like. So it's probing the differences in the smoothness, that anisotropy. And these were both space-based telescopes, remember, because this kind of light doesn't actually come through the universe. And wow, that came on really bright. So I'm going to turn off the COBE, off with the COBE, and on with the Wmap. right? So much higher resolution. Like, I don't even know how many times, but you can see, right? See for yourself, like the blobs are a lot smaller. We're getting a lot more granular in like the differences. And it's like we even threw in another color or two in there instead of just blue and pink. It's like there's also greens and yellows now. So that's pretty exciting. Um, so yeah, so that's the Wmap. But more recently, like just in the last decade, actually, I think this first one is almost 10 years old now, um, is the Planck. So the Planck data, which was from another, kind of bring this up a little more slowly, another uh, a space-based probe. If we turn off this one, we can bring up, uh, yeah, there we go. That's our Planck. Much, much finer detail, much higher resolution. So pretty exciting, pretty great. I remember the first time I got to show people this, like the first time it was shown live in the Hayden Planetarium, and like people cheered. It was like really exciting because it had just come out like earlier that year. I was like, yeah, it's really cool. So again, really great imaging of the baby picture of our universe. So we're getting, I think they've released like even more recent ones, but there we're kind of studying cosmology and looking at the early universe. So we're still in the microwave. So maybe we should move along and see some other wavelengths. We've done the visible, right? So you can skip that. But then the next longest wavelength I have, the next wavelength I have past the visible, or actually it's in the visible, is the H alpha. So that's a really fun one. H alpha, that's a hydrogen alpha. So again, that's another hydrogen feature. And this is showing us like a lot more of like star forming regions. So um, the atomic hydrogen, that was just hydrogen gas that's floating around the H alpha. This is kind of showing us more structure within our galaxy also, like where we have huge regions of gas that could be forming stars or whatnot. So we can kind of see like this really nicely outlines um, the the plane of the galaxy, which I think I've managed to flip turn upside down. I always feel like I'm upside down when I'm looking at the galaxy like this. Um, so that's one that we look at a lot. We see that one, I guess, quite a bit. It's one of the easier ones, and this isn't technically like not visible because it is. It's 656 nanometers, which is within the visible part of the spectrum, but just looking very closely and just detecting that one line intensely and then making a big map of it. So again, here the colors represent intensity. So just where you see like a brighter like white and yellow, that's just where there's more of it. And then like if we look kind of off the plane of the galaxy, we see there's not nearly as much off the plane of the galaxy. It's mostly in the plane of the galaxy where like these huge clouds of gas and kind of star forming regions are. So yeah, the last but not least is one I think I've loaded in here previously for another episode ages ago, and that is an X-ray. So this is the X-ray image from Erosita, which is I think ESA and Russian collaboration on this space telescope that's like way out in space. I think it might actually be at one of the Lagrange points. But so this one's way out there, and I'm actually going to kind of change our field of view again so we can see a little bit more, a little bit more of this in all its glory. Again, the X-ray, that's like really high energy. So I guess where pretty exciting stuff is happening. So we should be able to see things like if there were supernova explosions, and I brought my Erosita cheat sheet with me. So I might actually try to look back at some of these things. So we have, this was the Vela supernova. So that's in the constellation Vela. So that is a supernova remnant. We have, this should be like the Large Magellanic Cloud down here. There's a couple other, there's a cluster up in here. I think it's this one. Nope, not that one. This is the another, yeah, this is a Centaurus cluster. Oh, Crab Pulsar. So there's our nope, that's not the Crab Layer. This is nothing. This is, sorry. Centaurus cluster. I missed the Crab Pulsar, but I'm sure it'll come back around. I go ahead and rotate this. Whoops. Other way. I forget when we're like inside supposedly looking at the Earth and then kind of flipped her around. Yeah, you can see SCO X1, so Scorpius X1. So big X-ray source there in Scorpius. Again, this is kind of like the center of the galaxy in here. And I need to zoom out like even further. You just zoom out to like the whole thing. There's kind of this northern spur. Wow, maybe that's too far. Yeah, that might be too far. There's kind of this northern spur, this kind of loop of apparently very hot, very exciting gas. And then there's kind of a southern bit as well. But yeah, some really exciting X-ray sources that you can check out. So again, if you have OpenSpace, if you've downloaded OpenSpace, if you just like Google some of these maps, you can kind of explore the universe in great detail. There's Cygnus X1. So that's another X-ray source. That was one of our first black holes that we found. And this whole bubble. So if you're an observer, you might be familiar with kind of this whole region around Cygnus, that super bubble there. So that's just a couple of fun wavelengths, just the ones I either already had loaded in or the ones that I was able to load in on relatively short notice. But yeah, whoops. So thanks for still tuning in. I will get more organized at some point and finish up last week's and also post some current skies. So those are kind of summer projects for me, but happy that people are still interested enough to tune in to these Thursday evening tours. So thanks so much for joining me. Again, I'm Irene Pease, your friendly neighborhood astronomer. And of course, we've been using OpenSpace, which you can find and download for free at openspaceproject.com. Thanks so much. Be safe out there. Clear skies, everyone. And if you haven't gotten vaccinated yet and you can, please go get vaccinated.